Hello, my name's Adam Baker, Rocket Engineering and Cranfield University. This class is going to help you understand how rocket propulsion performance can be achieved and how ISP, or specific impulse, relates to two key parameters that we try and optimize and measure: CF, thrust coefficient, and C star. In this class, we'll cover how rocket performance is defined by ISP, and what that means for going into orbit. ISP, or specific impulse, being a measure of the conversion efficiency of chemical into heat into kinetic energy. It's based on two key parameters, C star and CF. C star is known as the characteristic velocity and is a function of combustion chemistry and very much dictated by the propellants that you choose to combust in chemical rocket propulsion. CF is the thrust coefficient, and it's related to how efficiently you design your nozzle and the external environment that you're operating in. These two together, but particularly the nozzle interaction with the atmosphere, leads to very different engine designs for space, where things operate in vacuum versus launcher engines, where things operate in the air, and also lead to the need for turbo pumps for launchers. Here's a quick recap of the rocket equation. You might remember that delta V, or the velocity change that you need to reach space, is a function of two things: the ISP, the propulsion efficiency, and the log to base E of the mass ratio, sometimes written down as ln of R. Okay, the mass ratio is the rocket's structural efficiency. We're not going to talk about that now. We're going to focus on ISP, or propulsion efficiency. How do we get a rocket engine to deliver high ISP performance? Well, it comes from two things. Firstly, the ability to efficiently combust and liberate chemical energy from fuel and generate heat in the form of molecular motion. This is all about thermochemistry, the choice of fuels and how well they react. Second, it's about acceleration. Firstly, from a standstill to sonic and then to supersonic velocity through something called the throat and then called the nozzle. Those two things can actually be looked at almost independently. C star, what goes on in part of the rocket engine called the combustion chamber, is really independent of the nozzle, but it's dictated by the propellants you choose and also how well you can mix and combine them together. The acceleration that you get from that, and hence the thrust coefficient, can actually also be treated independently of combustion, but is very much dictated by how well you design your nozzle and the external conditions. Inside a rocket engine, then, the things you're interested in are pressure and temperature and velocity of gas and how they change as combustion gas moves through a rocket engine. Inside the chamber, you have what's called stagnation conditions, and then you get rapid expansion and acceleration through to the nozzle. This leads to energy conversion. So at the start, when you inject the propellants, the thermal energy is high, the velocity is low. As you move the propellants, or as they move under their increasing pressure towards the nozzle, trying to escape from the engine and expand, the temperature and the pressure fall and the velocity rises. As you go through the throat and out the nozzle, the velocity rises again and the temperature and pressure fall further. So thermal energy ends up being quite low and velocity ends up being quite high. If you get this right, you will see something like this, where on the left we have a rocket engine being tested at Westcott and generating a plume of very fast moving gas, where you can see some structure in the form of diamonds within that, indicating it's moving at supersonic velocity. So first part of this is to liberate thermal energy, and you need an oxidizer, something containing oxygen or another highly reactive element. There's various choices, but pure oxygen is often the best. Hydrogen peroxide is another good choice, but many other chemicals have oxygen or an oxidizer within them. Many carbon-containing fuels are used to combine with that, typically hydrocarbons like diesel or petrol or aviation kerosene. Alcohols are good. One of the best fuels is hydrogen. Hydrogen liberates the greatest heat of combustion of any of the different fuels, but poses its own problems for handling. And selecting a good combination of a fuel and a oxidizer can give you a good C star. Here's an example rocket combustion chamber for space propulsion. We're going to start at the right-hand end here with the injector part. And I'm taking it off for you. The sole purpose of this is to allow a flow of fuel and oxidizer. The fuel's actually split into two parts, hence you've got three separate holes, to be injected and mixed and atomized and vaporized smoothly in the chamber. That goes on this end. The bulk of what we call the combustion chamber is actually the chamber part of it. So it's an area inside here where combustion is designed to go on smoothly to liberate chemical energy from the propellants. Then you have a throat here where the chamber tapers to the narrowest part, a little bit harder to see here, and then it expands into what's called an expansion cone to allow acceleration of the gases to maximum velocity. So we have injector, chamber, throat, and then finally nozzle. So how can the rocket engineer design to deliver a great C star, which is a key part of ISP and bringing things to orbit? There's a number of design options, ranging from propellants, which are stored in tanks outside the engine, the injector, the combustion chamber and parameters such as the diameter and the length, and how it converges to a throat, and how it expands to a nozzle and accelerates the gas. C star, remember, comes from liberating thermal energy held in the propellants in the chemical bonds and converting it efficiently into kinetic energy. And a lot of that's down to the injector. You can see an example injector here, which is really, in this case, like a very fancy shower head. It's creating a very fine mist of propellants together that are burning and mixing and liberating energy really efficiently. The other side of the C star equation is the need to use low molecular mass propellants, things like hydrogen, oxygen, and maybe a bit of carbon, but nothing heavier than that, because C star is a function of two things, and these are in a square root term as well. So T naught, or the combustion chamber temperature on the top, and the molecular mass of the exhaust products on the bottom. And it's not a strong function of those because you're looking at those inside a square root function. So what that's saying is you have to really take the temperature very high or make the molecular mass very low in order to get a big boost in C star. So it's pretty hard work for the designer. But this is what a modern rocket engine looks like. And you can see a large nozzle here. We'll come on to that later. A combustion chamber held by my thumb here. And upstream, there are some valves designed to let propellant in. And what's a bit harder to see is actually the quite sophisticated manifold and injector designed to push propellants efficiently into there and do something really neat, which is cooling the engine. Now, why do we need cooling? Well, this is partly due to something called the flame temperature. Rocket propellants burn really, really hot. How hot depends on a couple of things: what propellants you select and how they're mixed, or the mixture ratio. This is the fuel to air or fuel to oxidizer ratio. Here's an example of two propellants: H2O2, hydrogen peroxide, and RP1, which is a refined form of kerosene. And on the vertical axis, you can see the flame temperature that's achieved when you mix those. And on the horizontal axis, the flame temperature is driven by the mixture ratio by mass, or oxidizer to fuel ratio, or O to F as it's sometimes called. If you look a bit more closely, you'll realize that the peak temperature is around about a mixture ratio of 7.5 by mass. But what this results in is a flame temperature of 2800 Kelvin, or more than 2500 degrees centigrade. That's pretty hot. Those propellants, by the way, were used in the Black Arrow launch vehicle, which was Britain's so far only foray into the world of launch vehicles in 1970 and 71. Now, taking a look at a different set of propellants, this is oxygen and hydrogen. Plotting, again, using a thermochemistry program, the same comparison of mixture ratio against flame temperature, you can see that the peak mixture ratio, or the peak of temperature, is at a mixture ratio of about 6.5, not so very different, although this will vary a lot depending on the propellants, but the peak temperature is closer to 4000 Kelvin, okay, or over 3,500 degrees centigrade. That's quite a lot hotter. And this is typical for a rocket such as ESA's Ariane launch vehicle. And remember, in order to get a high C star, you're trying to make that flame temperature as high as possible. So things like oxygen and hydrogen are definitely favored. There are propellants that run cooler, making it easier on your engine, as we'll see, but you get lower performance as a result. So it's a difficult challenge for the designer. However, we can play some games with that, with something called cooling. So remembering that rocket flame temperatures, or the temperatures that propellants burn at, are between 2,000 and 3,000 centigrade. What does that really mean for engineering around that? And these are the temperatures that are typically reached in the throat of the engine, where the hot gas is being compressed the most and starting to accelerate, but hasn't converted its thermal energy into kinetic energy. Well, typical materials that you might find in a rocket engine, mostly metals, niobium, Inconel, which is a nickel-based alloy, stainless steel, titanium, and aluminium, all have a melting temperature well below what you might expect to see in a rocket engine. So that's the problem number one. How do you stop the material melting? And actually, most materials, metals particularly, become soft and therefore mechanically not very reliable, well below their melting temperature. The other challenges that you face are you have to prevent them oxidizing, which might mean they would fracture or disintegrate. They need to be formed into the right shape and joined between different parts of the engine. So you can see there's some valves, there's an injector, there's a combustion chamber, there's a big nozzle here. All of those are made of separate parts and joined together. And how much, of course, these materials cost is really important, with things like aluminium being cheap, but having a very low thermal tolerance, and materials like niobium and Inconel and titanium being much more expensive. And the way this is dealt with is by cooling, and we'll see a video a bit later showing you how cooling can be used on the inside of the engine to reduce the peak temperature at the hottest part of the engine, which is the nozzle. And you can see this banding is an effect of the cooling. We'll come back to that. What cooling can actually achieve in terms of benefits is really pretty extraordinary. So here's an engine manufactured at a place called Westcott in the UK, and this is a cross-section taken through it using a thermal camera. And the camera shows you that as you go from the exit plane of the chamber, you've got a high temperature. It's around 700 degrees, so that's still pretty hot, much, much hotter, but you're peaking at around 1,400 degrees centigrade, which is a long way below the temperatures you might expect to see for peak combustion. And the reason for that is that there is cooling going on. And in fact, it's a very neat trick called fuel film cooling, where fuel is dribbled down the inside of the chamber wall and it forms kind of a protective curtain or film around that. And that enables this kind of engine, the Leros engine currently made by Nammo at Westcott, to run white hot and not deform and not melt and not disintegrate, and do that for several hours at a time. Really spectacular. Fuel film cooling is explained in a few minutes. Now, the other thing is that this does cost you some C star and hence ISP performance. So you've got to find just the right balance of fuel film cooling to make it work and give you some benefit to the engine. The choice of propellants is also pretty important. As mentioned earlier, you've got various different oxidizers you can use. So these contain oxygen or some other highly reactive element. Pure oxygen is generally the best. Hydrogen peroxide is a nice dense way of storing lots of oxygen. And there are various forms of oxygen combined with nitrogen in the form of the acids, the nitrous and the nitric oxides, which are increasingly difficult to handle and often quite toxic, although N2O, laughing gas, is quite a good one to get started with. There's some choices here, but really you've got to have oxygen in there. There's a lot more choice in the fuels, and most of them contain carbon. So things like kerosene, methane, propane, the various hydrocarbons, also alcohols, and occasionally hydrogen can be used, but that's a particularly difficult fuel to handle. But at least there's a range of choices there. And remember that what you're trying to do is combine these two in the most efficient way to get exhaust products that have low molecular mass. You want them to burn hot and have low molecular mass, because C star is a function of T0, the combustion chamber temperature, and the molecular mass. And if you look at some typical exhaust products from a rocket combustion chamber, you might see water. Hydrogen may come out the back, it's not all fully burnt. CO2 and CO are quite common. And what you can see from this is that things with hydrogen are generally pretty good. They have a low molecular mass. And in fact, actually pushing some hydrogen out the back of the chamber unburnt is a good way to increase your C star and actually reduce your flame temperature. On the other hand, things with carbon and heavier elements are not so great. Okay, so it's down to the designer to decide how to find the right balance of rocket propellants with oxidizer and fuel that give you a nice hot temperature that can be cooled so it doesn't melt the engine, and a low molecular mass in terms of the exhaust products to give you the best possible C star. Here's an example of the fuel film called Leros engine. In fact, the larger Leros 4 space engine developed by Nammo, which I worked on, using hydrazine and nitrogen tetroxide storable propellants. And another example of a large fuel film cooled engine from Sheffield University. Now, Dr. Ian Coxhill, Chief Engineer, Nammo Space, on rocket engine cooling.
Okay, Adam, so what you're looking at here is the inside of a Leros 1B engine, and you can see the pattern generated by the fuel film cooling. So these rocket engines operate with a core combustion temperature of about 3000 degrees C, and the melting point of the material is little over 2000 degrees C. So we need to do some kind of cooling to ensure that the metal doesn't melt, and we do that by spraying fuel onto the inside of the combustion chamber. That does two things. One, it forms a film, which you can see by these petal patterns, but once it's boiled, it also forms a gas layer, which is downstream of the liquid layer. Both of those actions, both the action of the liquid flowing over the surface and also the gas which is formed, insulate the surface from the main combustion flow and keep it to a peak temperature of about 1350 degrees C.
Earlier, we talked about how important C star, or characteristic velocity, is to rocket performance. But how do we actually measure this and find out how good our rocket engine design is? Well, in a typical rocket test rig, you'll find a number of sensors to measure things like pressure, how much rocket propellant is flowing through in mass terms per second, what the thrust is, technically called a load cell, and thermocouples to see how hot it's getting and how well your cooling is working. All these collectively enable you to measure C star and ultimately compute ISP. Here's a typical rocket engine test rig. This is Airborne Engineering at Westcott, who are one of the most experienced companies in the UK at testing rocket engines for a wide variety of customers. They've actually got two rocket engines set up on the test stand there. There's a hybrid rocket engine, the long black cylinder on the left, and there's a bipropellant liquid rocket engine, the short stubby grey cylinder on the right. And they won't test both of those at the same time, but they can be tested on the same stand. And that's James McFarlane, who is the owner of Airborne Engineering, getting ready to load some propellant for testing of the pulsar hybrid that you can see there. Now, C star can be experimentally measured according to the following. It's actually a product of chamber pressure and throat area divided by the propellant mass flow rate. So if you can measure the chamber pressure using a pressure sensor, you can measure the throat area, which you can do with a set of vernier calipers, or you can just check it against your design. And if you can measure the propellant mass flow rate, you can compute C star. So that when your rocket engine fires, you can find out how efficiently that all-important combustion is doing. But remember, ISP is not as simple as that. It's defined as a velocity, but it's a combination of two key things. So on the left, how well the propellants are combusted. That's internal to the engine and very much down to the propellants and the mixing and the efficiency of that. But it's also a function of how well the gas produced is then accelerated, how that thermal energy liberated from the chemical energy is converted to kinetic energy. And a lot of that comes down to how well the pressure is managed by the nozzle design. So, looking at that in a bit more detail, where's the benefit of the nozzle? The ISP comes from, firstly, the chamber C star, gas accelerating to sonic velocity at the throat, and then trading pressure for further velocity to go supersonically in the nozzle. So the chamber part of it, that's more or less the same diameter until you quickly narrow down at the nozzle, provides the C star. As you get to the throat, this is designed to accelerate the gas to Mach number 1. This gives momentum thrust, a thrust that is purely a function of the momentum, or how fast the gas is flowing and how much mass you've got flowing. But there's more to it than that. The nozzle accelerates the gas to greater than Mach 1 to supersonic velocity, augmenting the thrust with pressure thrust. And the combination of momentum and pressure thrust provide the coefficient of thrust. And it's really how much pressure thrust you can get that defines CF. So, as a reminder, ISP, the efficiency of your rocket engine, or how fast the gas is flowing, is just a simple product of C star, which is all about combustion, generating what's called enthalpy, and then CF, which is how well that enthalpy can be converted to kinetic energy. Looking at it in a bit more detail, again, to remind you, CF is a gauge of how well nozzle converts that enthalpy into kinetic energy. CF can be simply defined as the thrust divided by the product of the chamber pressure and the throat area. The nozzle CF adds to the momentum thrust. So you have the following equation where thrust, or F, is mass flow m dot times the velocity at the exit, that's the momentum component, plus an additional factor which is related to the difference between the exit pressure and the external pressure times the exit area. And you can see that as the exit area of the nozzle gets bigger, that external pressure component can also grow. But it also depends on the balance of the pressure your rocket engine's generating as the gas leaves it versus the external pressure. So thrust coefficient is a function really of gas properties. They don't vary that much with different propellants, but the nozzle area ratio, eta, the quotient of the chamber pressure divided by the exit pressure and the external pressure. Remember though, it doesn't depend on gas temperature or the combustion properties. That's the C star. If you plot some of this in a program such as Excel, you can see the following. So for different values of P0, or the internal chamber pressure, okay, you can see how as you change the area ratio of the nozzle, or basically making it bigger, you can increase the thrust coefficient. Think of CF as a multiplier of your C star. So if you have a C star of, say, 1,000 meters a second, a thrust coefficient of 1.5, your effective ISP, or your exhaust velocity, is 1,500 meters per second. And these are for given values of gamma, which is a product of the propellants, and the ambient pressure, which in this case is set to sea level, or 0.1 MPa. That's 1 bar. So what this shows is the combustion pressure effect on CF, the area ratio effect on CF, and actually you get the maximum CF, that's this white line here, when the exit pressure equals the ambient pressure. CF can vary between more or less 1 and 2 and can effectively double the velocity, or the ISP, of the engine. And this is why in our earlier picture of the engine, you can see that this small engine with a very narrow throat has a very large nozzle, because it's designed to operate in the vacuum of space where the external pressure is almost zero. And by expanding the internal gases until their pressure drops to zero, you can gain maximum benefit of C star. The challenge for launcher propulsion engineers, because that was a space engine we showed you earlier, is that the atmospheric pressure constantly changes as you go from the launch site, which is typically at sea level, up into space. So from 0.1 MPa at sea level to almost nothing in space. And you can see the atmosphere pressure being plotted as you go up in altitude just to a mere 10 kilometers. And that's only about 1/10 of the way to space. So at 1/10 of the way to space, your atmospheric pressure has dropped to about 20% of what it was. And that's a real challenge, because the external conditions affecting the flow of gas through the nozzle, and hence the CF and the C star are going to be constantly changing. So rocket engine nozzles need to compensate for this to maximize performance, but it's very difficult to do that with a fixed nozzle. But in order to get best thrust and ISP, that's what the engineers have to think about. Here's an example space engine compared to a sea level engine. So you can see the sea level engine test is here. You can run that video there, and you'll be able to see this in a moment. Yeah. So there's some particular parameters being put in there. Okay, mass flow rate, mixture ratio, fluid to cooling. And you can see that very rapidly, very nice smooth stable combustion here. The engine starts to flow right up due to the effect of that thermal energy being liberated from the chemical energy of the propellants. We'll stop that here. But if you compare that engine, which is a sea level or ground testing one, with the final engine, this is the Namo Leros 4, being optimized for vacuum, there's an enormous great nozzle being added to extract maximum velocity from those combusting propellants and really increase the CF to give the best possible ISP. And that's the difference between a space engine and a sea level engine. And it's also one of the reasons why launch vehicles need pumps, which we'll come back to in a later class. Here's Dr. Ian Coxill again on rocket nozzles.
An idealized, optimized rocket engine is one where we get as much velocity out the back end of this engine as possible, and we do so by expanding. And that's the reason why there's an expansion chamber on it, and all high performance space engines follow this trend of a big expansion cone on the business end, which is the combustion chamber portion.
To recap then, firstly, chemical rocket engine performance, is different from electric engine performance, which we'll talk about in another class, is defined by ISP, or specific impulse. Specific impulse comes from two parameters, C star, characteristic velocity, and CF, combustion, CF, which is thrust coefficient. C star is a product or a function of combustion chemistry, the molecular mass of the gas, and the energy released. Hydrogen oxygen is a really good propellant combination for C star, but it's quite difficult to handle for all sorts of reasons, such as the propellants are cryogenic. CF is really related to how well the gas generated in combustion can be accelerated to a high Mach number. It's really a function of the pressures inside and outside the engine. So you have control over the inside pressures, but not so much over the outside pressures. And that can make life really hard for the nozzle designer. But basically, space engines make use of large nozzles and work at low pressures against an external vacuum to increase the CF. Launcher or booster engines generally use pumps to give them high internal pressure working against external air pressure. And both parameters can be experimentally measured to gauge effectiveness of design, such as at places like airborne engineering at Westcott. Thank you.